So what I'd like to talk about today is logistic regression, which is a technique for doing classification using linear models. Again, we've so far talked a lot about regression. Regression problems are ones where we're trying to predict a numerical value. Classification problems, we are given collections of examples that are labeled, okay, in some way. Is someone a male or a female, a Democrat or a Republican? Is is a tissue sample cancerous or benign? Okay, and typically, these are binary. In the most vanilla version, these are binary classification problems. The classification problem is you were given an input record, a set of features, and you want to know what label it is. And my claim, first of all, is that we could use linear regression to build classifiers by converting class labels to numbers. Okay, we could take our classification, our two classes, and assign, in the case of binary classification, and assign each of the so-called positive class members labels of 1, and the negative classes, okay, labels of 0. And now, in some sense, you could think of using linear regression to try to predict the number associated with the class, okay? Again, typically, when we talk about defining classes, we think that the positive class gets 1. What is positive? Positive is usually the smaller class. Positive is usually the thing that we are looking for somehow. So in the case of like the 4 examples I have here, spam seems to be the thing that you're looking for. Cancer seems to be the thing that you're looking for. In the cases of male, female, and Democratic, Republican, these are presumably classes that are roughly equal in size. There's not one that is, kind of special, but one of them gets a class of 0 and one gets a class of 1. Any questions about that? So if we do this, one way that we could use regression to try to identify classes, okay, is to say that there's going to be a 0, that all positive examples, remember the y value was 0, so these were the positive ones. All examples with a negative value would be 1, okay? Here we have, let's say in this case, we're assuming we have an x, we're trying to make our prediction of class based on some variable x, or it could be a vector of variables x, okay? Linear regression would try to find the line that best fits this data, okay? In this case, the red line is what best fits this data. And if you look at that, it has certain good properties that might suggest this is a way to do classification. If we say that basically anything that gets a value of y, we're now trying to figure out a function y is equal to f of x, okay? If y is greater than 1/2, we can call an example positive. And if x and if y is less than 1/2, we can call it negative, okay? Does everybody see that in this particular example, okay, the regression line would actually do a good thing, okay? In this case, we happen to have all the positive examples, x is greater than 0, okay? And if we note in this particular regression line, for all x greater than 0, the y value is greater than 1/2, okay? So does everybody see that we could do classification this way? What let's say, is not good or right about this way of doing classification? Can anybody see any limits here? Or are people perfectly happy doing classification here? Okay.
Could you clarify which one is the regression line?
The regression line is the red one. Okay, we want the best fitting line to meet, we want the line that best fits these points. Okay, remember, what did the regression line try to optimize? Remember, we were trying to summarize the, minimize the least squared error. Okay, the least squared error is here. We sum up the square of those residuals. And the claim is that this red line is the line that fits that data the best. Okay, in terms of minimizing the least squared error. Okay, do you have another proposal for a line that would fit it better?
Well, yeah, with that red line, if we were to try and derive classes from it, isn't it only 50% accurate? Wouldn't the green line perform
This
better for
red
classes?
line would be 100% accurate. Okay, that's what I want you to see. We are going to say, I'm going to interpret the y-axis as the probability of being a positive class element, right? One was where the positive examples were, right? So in this case, what do we get when we look at this point over here? For this value of x, what do we get? The probability of it being positive is, it looks like, something like 0.65. Are we going to call that 0.6 positive?
Yes. Okay, I see.
I think I'm going to call it positive, right? So does
Yes.
everybody see how this formulation, in principle is trying to do something? Okay. Now, are there any issues people have with it? Okay, one thing is, there's on the chat, there's a notion here about, well, if you want these to mean probabilities, then notice you're allowing probabilities that are greater than 1 and less than 0. Okay, so it isn't really certainly a good example of probabilities. Okay, and that one I can kind of guess. Okay, any other issues with this kind of a formulation? Okay, what happens if I add another positive example over here? Okay, did everybody see that positive example? What is, again, x, I'm assuming x goes out to here, and this is going to be, if I did it right, this is 35. What is going to happen to the regression line if I give a very, 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 very positive example? The residual is going to be very, very large on this line. The square of the residuals is going to be very, very large. What is the regression line going to want to do? I claim that to minimize the least squared thing, it is going to bend towards that. Maybe it's going to come out something like this. Okay. And if we look at it, does everybody see that adding a very, very positive example makes the regression solution worse? Adding an outlier you feel unbelievably confident about, okay, has the undesired effect of making the classifications worse. Okay, so what we really want to think about, again, I'm kind of enjoying marking a lot of stuff on the colors on it today. What we really want to do is, instead of thinking about a line that kind of fits what the labels are, we want to try to find a boundary that will separate the two examples, the two sets of examples. And so classification is less a problem of trying to predict a number, but trying to find a separator between regions. Any questions about that? So again, in our dream, what we're going to have is, again, remember that in that again, when we were thinking about regression, we typically have a y value that's our desired thing and our x value that is our features. We can naturally in drawings represent the two-dimensional figures, okay, by simply coloring the points. We can think of it as, if let's say, if we think of a classification problem in 2 dimensions, we can think about the points as being, examples, and we can have 2 different kinds of points. Here we have the dots and the squares. What we want to do is to find what is the best separator between the classes, okay? And thinking of things in terms of separators is a good idea. What happens to the separator when I give you an example, what you call it, a positive example out here? Should a positive example out here, really that we really know is super positive, okay? Should this change the boundary? Okay, I think it should be clear that that does not change the boundary, okay? And that in fact, the place where the boundary is kind of most important are kind of the examples that are kind of close, where it's relatively, where they're relatively similar to each other, positive and negative examples. That's where the work of the boundary should be done. Any questions about that? So what logistic regression is a method that will use, some of the, some of the formalism and machinery of linear regression, but it will find the best separating line for a given training set. Any questions about that? So first of all, I'm going to be talking about logistic regression as finding the best linear separator. But recognize that all the tricks that we can use for nonlinear separators, okay, to find nonlinear, to make linear regression take advantage of, be able to fit nonlinear functions if we give them the right features, this will still apply. If we look at a set of points here, okay, if we have here an x and a y, and we have the circular, if we look at this, the dots are all near the origin, and the y and the squares are kind of on the outskirts of it. It should be clear that the right separator we want here is actually a circle. Is there a way we can add to our feature set x1 and x2 so that we would be able to find a good circular classifier of this? My claim is that if we have x squared and y squared terms, x squared and x2 squared terms, one way to think about this is if we have x squared and y squared terms, x1 and x2 squared terms, the points that are further out, if we have a function like x1 plus x2, x1 squared plus x2 squared, the points that are further out are going to get a big value here. Does everybody kind of see that? And so I could imagine a world where now, if I looked at these points from the side in x1 and x squared and x2 squared space, it's hard for me to draw in 3 dimensions, but what we would end up having are these dot points would be down here. Those are the circled ones. And the boxes would presumably be out here. It's kind of a paraboloid. And in that case, there would be a linear separator. The small values of y would be the dots, and the big values of y would be the boxes. So if we want nonlinear decision boundaries, if we know what nonlinear features we care about, logistic regression will do just fine. Any questions about that? But for now, I want to talk about how logistic regression works. Okay? Any questions? And logistic regression takes its name from our friend the logit function, which we've talked about a couple of times here. What was the logit function? Well, here I have a slightly more general logit function than I had before, where I've got a constant c over there. But a logit function is something that takes an x variable and converts it to a probability. The properties we want is that when x is 0, okay, what you call it, when x is 0, the probability is going to be a half. Again, we're going to think of the logit function as telling us what is the probability that this value x is positive. Okay, and when we have a value of 0, we're going to say we don't know anything. When we have a very, very positive value, it's going to go to 1. And when we have a very, very negative value, it's going to go to 0. And in particular, if we look at this function, this does the right thing. Again, when x is equal to 0, e to the 0 is 1. 1 over 1 plus 1 is a half. That's what we want. When x is very large, okay, e to the minus something enormous is going to approach 0. So 1 over 1 plus something like 0 is 1. When e is very, very negative, when x is very, very negative, the negative to the negative is going to be a positive. E to the big number is going to approach infinity. So 1 over that is going to approach 0. Okay? So the logit function has the properties that we want for giving us a probability, okay, as a function of x. And this constant c here is what's going to shape how quickly does it get there. As you can see, once you get very large or very small, it asymptotically approaches, 0 or 1. This constant c is what's going to determine kind of the steepness of the transition. Any questions? So what is the idea of logistic regression? We are going to generalize this, if you looked at, was a linear model, okay? Where again, we were given a value of our variables x and our coefficients were w. This was a linear model just the same way it was in our linear regression. But now what we're going to be using it for is not as a value by itself, but we're going to plug the value in as our exponent, okay? And we're going to be trying to get basically, we're going to basically take, once we have got these coefficients, okay, we can take our input parameters for everything else. This will map it to a score. The logit function will map that score to a probability, okay? And so logistic regression, we want to try to find what are the best coefficients here, okay? So that we get as accurate a classification model as we can. Any questions? So how do we come up with, if we think about it, how do we come up with a criteria for this? Okay, we need some kind of cost function for what it means to be the best fitting classifier. Okay, we're going to assume that our training examples, we have n training examples, and they are either labeled positive or negative, which we're going to, again, determine as class 0 and 1. Okay? And we are going to try to come up with what are the coefficients, the value of the coefficients W, that will give us a high probability of being positive on positive items. and a low probability of being positive on negative items. Okay? So we need to now come up with a cost function that will assign a probability, okay? Will tell us how happy are we with a given probability for a member of a different class, okay? So what is our cost function going to be? In an ideal world, if we were being greedy, okay, we might say that we want our classifier to what you call it? Oh, okay. Before we talk about what we want as ideal, okay, what is the cost function that we're going to use in logistic regression? I'm going to claim a cost function that has this kind of property to it. Okay, we are going to want our cost function to tell us basically as a function of the probability that we give and the label that the object actually had, what should the cost problem function be? Okay. If the item was positive, okay, remember we're interpreting this as being the probability of being positive. And this is going to be the penalty or the cost, okay, for guessing this. Now, if our example was actually positive, okay, we want the penalty to be 0 when we get it right, okay? If we say that this has a probability of 1 of being positive, okay, then if it's actually positive, we should pay no penalty. We had no doubt. Again, there's an election today. Okay, there's going to be a result one way or another. A forecaster could tell you who's going to win, but they also need to express a level of confidence. The probability is a question of what the confidence is. Okay, and the best prediction is if you say that the result is going to be positive, and you're so sure that the probability is you assign it a probability of 1 of happening, you should pay no penalty if you're wrong. Okay? You should pay a gradually increasing penalty. Okay? Based on how confident, how confident you were. Okay? If you said that there was a 50-50 chance of it being positive, and it was positive, you should pay a penalty for that. That's kind of what this function is saying. But on the other hand, when you get it wrong, you should pay an even greater penalty. And if you are absolutely certain that it was positive, okay, or that it was negative, okay, and which means you said it was a probability of 0 of being positive, and it was positive, you should pay a potentially infinite penalty. So the shape of what we want is a function, is a penalty function like this. Does everybody kind of see that? Or at least this is a plausible kind of penalty function that we would pay. Can anybody come up with another plausible penalty function as a function of guessing positive? Okay. One possibility might be you get no penalty for getting it wrong, and then you get a high penalty. You get no penalty for getting it right, and a high penalty for getting it wrong. Okay. This would be an alternate penalty function. Why don't we like this penalty function as well as this penalty function? Anybody see why this penalty function is, do people like this penalty function? Where if you get it, the label wrong, meaning you would have, if it was less than the probability of, if you think that the probability of it being positive was 0.49, and if it was 0.49, if you faced as big a penalty as if you had gotten it at -1, if you had thought there was 0 chance of it, this is giving you a big penalty on the tough examples, the ones that are kind of right by the boundary. Okay. This way, again, first of all, it's not smooth, so you get problems with whether this is going to be convex or not. Okay. But the other problem is that it seems like a very, very harsh thing. That on an example you really weren't that sure of, you would face a very, very big penalty. Any questions? If we believe that, okay, here is the cost function. Okay. Suppose we know, let's think about what the log function does. The log of 1, remember, is the exponent, okay, that you have to raise 1 to, okay. What is the log of 1? Okay, it is the exponent that you need to get something to be equal to 1, okay. But if you have x to the 0, x to the 0 is always going to be 1. So the log of 1 is 0. Okay, and this is the correct cost that we want for positive items. The log of 0, well, let's think about it. What is the log of, if we think of these as base 2 logarithms, just because of it? The log of 1/2 is what? Base 2 of log of 1/2 is what? It's going to be -1. The log of 1/4 is going to be -2. As x gets closer, smaller and smaller, okay, the log gets more and more negative. The claim is the log of 0 is -infinity. If you believe that, this gives us exactly the positive cost function that we had on the previous slide. Okay, at 1, the value is 0. Okay, at 1/2, the value is, in this case, 1, or close. I guess it was, let's say close to 1. And as it's 0, it becomes infinite. Okay, if we take the negative log function, okay, this does what we want. This gives us the cost function for all positive examples. If we want the cost function for negative examples, what we've got to do is basically just reflect this function. Okay, if we now have a negative example, we want to pay an infinite cost for say, having a high probability of it being positive. And we would like to pay 0 penalty. Okay, if if it was a negative example and we said the probability of being positive was 0. To achieve the blue line, all we need to do is to reflect it. Reflecting it is basically just taking 1 minus the input value. Okay, any questions about that? Do people see how this log thing gives us perfectly reasonable, has the advantage that it gives us more of a punishment the less accurate our prediction is? Okay, any questions? That said, what is the final cost function for logistic regression? Okay, this is the cost that we wanted to pay on a positive example. This is a cost we wanted to pay on a negative example. Okay, now note that if we said a positive example was 1, okay, if that a positive example was 1 and a negative example was 0, if we actually had a positive example, if we multiply yi times the penalty for, let's now consider the iterating example. If yi is the label of that example, we would like to use the labels to decide which cost function we should use. If the example was positive, we want it to be this function. Note that if positive meant 1, if we multiply yi times the positive thing, penalty, plus 1 minus yi times the negative thing, if yi was positive, this becomes 1 and this becomes 0. If yi is negative, okay, this becomes 0 and this becomes 1. Because yi is a class variable, okay, it is only going to be 0 or 1. So we don't have to worry about combinations of these things for some y like 1/2. We know that our y's we care about are always going to be either 0 or 1. By using this trick, we weigh the appropriate penalty function. Does everybody see that this gives us the cost function that we want? For each example, okay, we figure out what the penalty is. This 1/n thing is going to be the the average penalty, okay, which I guess we don't really need, but this will tell us what is the average penalty per point. Okay, any questions? And so if we minimize this loss, we are going to be finding the best possible coefficients of a model. Any questions? Okay. Now it turns out that this this cost function is a convex cost function. So just like in last class where we showed that we could use the gradient descent search and stochastic gradient descent search to find the optimum values of the parameters. So we could do that with logistic regression, okay? And so this will give us an efficient way to find the best linear separator between two classes. Any questions? The example I like to show, which we'll see again in some other contexts when we talk a little more about classification. Here's one where I've got examples of men and women, okay? And we have each as represented as a point in height weight space, okay? So each point, it looks like the blue points are male, the red points are female, okay? And generally speaking, women tend to be lighter and shorter than men, okay? When we ran logistic regression on it, this was the separator we got. And in this case, okay, it was able to classify the, about, in each of the regions, it classified about 3/4 of the points correctly, okay? Any questions? And again, if we looked at it, a example like this, okay, which is a woman far from the boundary, okay, helped shift, contributed a lot to shifting the boundary in that direction, okay. On the other, and again, the bad examples here would be men that were, again, far from the boundary, okay? But as we noticed, the number of misclassifications in this case happens to have balanced pretty well, because that way, the wrong classifications here are pulling the line in this direction. The wrong classifications here are pulling the line in that direction. And this is where it balanced. Any questions about logistic regression and how it worked and what the cost functions are? Okay, fair enough. So if I want my bread and butter classification method, just like I think linear regression is a good first type of machine learning model to use for regression, I think logistic regression is a good baseline model for classification. Any questions? Okay, that said, there are a few issues that come up with any classification problem. And you know, uh, you know, again, logistic regression is no difference. We have to worry about whether class sizes are balanced. We have to deal with the fact that there sometimes are non-binary classification problems. We have more than a bunch of classes, and there are techniques for dealing with that. And also how to interpret probabilities in the case of multiple classes. So these are what I would like to talk about for the rest of class. So the first thing to see is that classification problems are much easier and much more sensible when you have roughly the same number of positive and negative examples. Okay? If you don't, imagine a world where, let's say, we had let's say we had one positive example and a million negative examples over there. Where do you think the separating line between the positive classes and the negative classes should be? If you guys were voting, if this was your world, where would you want the separating line to be?
Probably like in the middle.
So a logical thing to hope would be to want the separating line to be in the middle, okay? Because it is going to because kind of it provides the biggest gap between the examples on one side than on the other side. Where will logistic regression want to put its separating line? Anyone have a sense of where logistic regression is going to want to put its separating line?
Probably really close to the negative examples.
I think it's going to probably be here because, first of all, the further it gets away from all the negative examples, the happier all these negative examples are. So there's a million examples getting more and more close to their penalty is getting more and more close to zero. Every time you move this line further here, the penalties for each of these points gets closer to zero. The penalty that you get as you move this line closer and closer to the positive example, this one is going to pay a penalty, okay, for it. Its penalty is going to decrease also as you move towards the right. But ultimately, the force of the million points is going to outweigh the force of the single point, okay? So if you have grossly unbalanced classes, it's going to try to just go and cover the bigger class as easily as it can. Okay. So in our dream, we would have the same number of positive as negative examples if we did a classification problem. Why don't we sometimes have the same number of positive and negative examples? Okay. Why might we have an unbalanced class situation? Well, often it may, yeah.
If there's sickness, right? Like not everyone is sick, we assume.
So again, if we think about it, like let's say in the cancer case, there simply are more people who are healthy, thank God, than have cancer. Okay. So if you have those examples, it's often the case that it's easier to find positive examples than it is to find negative examples. Okay. So the question now is, what should we do about unbalanced class sizes? Okay. I am going to claim that there are a few techniques that are reasonable to try. One is to go and work harder to find examples of the minority class. Okay, in the cancer example, how might we go work harder to find more examples of people with cancer? Well, maybe it's talking to more oncologists to find more patients. Okay, maybe anyway. So we agree that the dream solution is that sometimes if we don't have as many, positive examples as we would like, part of that says that you've got to, work harder and find more positive examples. Okay. Now that doesn't always work, but but obviously that's an option. One way to create a more balanced class might be balance things are to discard elements from the bigger class. Is this a good idea or a bad idea?
I mean, undersampling can be good as long as you're careful to not throw away really indicative values. If you do like a PCA first and only, maybe get the nice values before, it might be better.
Okay, so the claim here is that well, first of all, throwing out positive examples throws out data, and so there's part of us that should rebel against that. But the other thing you're saying is a difference between good and bad examples. What do you mean by a good or a bad example?
Basically, like, with data, we can find that a lot of data is very similar to other data. And so we want, really differentiated data or like highly
Okay,
varied data.
so this is an interesting question. Which examples, here we've got a small number of positive ones. Here we've got some negative ones. So one argument would be that if you're going to throw them out, maybe you should look for an equal number of representatives. Okay, the representatives being if you have very, very big class, big clusters here of things that are very, very similar. Your argument would be that if you throw out one of the ones that are very similar, this will have little effect on your model, or less so than picking a more distinctive example. So one criteria that you're proposing is to throw them out based on, kind of how rare they are. Okay. That seems like a good case if there really are a lot of duplicates. On the other hand, the rarest examples are probably outliers. Okay. And so one problem is that if you look at the ones, if you took, let's say, the most separated examples possible, you will probably overweigh the weird things. Okay. Might be a good idea, might be a bad idea. Are there any other criteria to decide which ones we favor?
Could you just do random?
You could do it randomly, and if we did it randomly, then we would, oversample the common things. Randomly seems like a way to do it. Are there any other examples, though, that seem like they are the most interesting examples? Okay. Part of me says the ones that are closest to the decision boundary are the ones that seem most interesting. Okay. Those are the ones that you would really want to keep. Okay. And so you could imagine other kinds of class things where maybe you build a separator. You find which ones are closest to the decision boundary, and then you retrain on those. Okay. So there are different tactics for this. But one idea is, we may very well want to delete elements from the biggest class in a couple of different ways. Ideally, it's important to keep the ones that are near the decision boundary, because those are the ones that really should be the ones shaping it. Okay? Any questions about that? Now, another idea which I like, okay, is don't actually discard the members of the minority of the larger class, but weigh the elements more heavily. Does everybody kind of see that if we we have two, let's say we have twice as many, we have 2x negative examples and x positive examples. If we weigh each positive example twice that of a negative example, then logistic regression is going to want to make the positive examples happy. It will have an equal incentive to do this. Okay? So one way to do this is the easiest way to to weigh the minority class more heavily might be to just make copies of these points. If I want to make the positive examples twice as important, one possibility is I add two, I replicate each point. And now I've got 2x and 2x examples, okay? And so one thing is you could do it by replicating the points exactly. Better is that the logistic regression formalism and most machine learning formalisms, there would be a parameter somehow where you can weigh the example by how important it is, okay, and use that as a coefficient in the optimization function. That's better than actually constructing the examples explicitly, because first of all, if the difference was, if it was 100 times more negative examples, constructing 100 times positive examples is going to, create a lot more work for the algorithm. So it's better if you're determined to replicate points, weigh the current examples more seriously. It's better if you can do it by adjusting a coefficient, okay, in your solver, rather than by actually replicating the points. But if you have to, replicating the points is a way to do that. Any questions? Another idea is that if you're going to replicate the points, okay, it's maybe, replicating the points exactly gives this example more heft. But if you add if we add 1 point against 1,000,000 points, replicating this point 1,000,000 times, it's really going to overfit, okay, what an example of a negative of a negative example is, or a positive example is. Better is if you can kind of construct artificial examples around your point, okay, by adding, let's say, small amounts of noise or variation, okay, around the point that you have, and call these artificial examples positive. That can be a more robust way to do it. Of course, the best thing is to actually get enough data that it's balanced, but these are all reasonable techniques. Any other ideas of what to do if the data is not balanced? Okay, good. The other issue that comes up a lot in multi-class classification, is that classification tasks are not always binary. Again, you guys worked with movie data, okay, and often the movie presumably had one of the labels that you had was a genre label, okay, and you could imagine a typical classification problem is that you would like a to try to predict what the genre of something is. Those things are multi-class classification problems. Any questions? Now, what should the decision boundary look like for a classification problem? For the binary classification problem here, okay, it's just a separating line. What should what do we think that the decision boundary should look like for a 3-class classification problem like this? Okay. I'm going to say that in an ideal world, you would be trying to learn something. Maybe that is a classification boundary like this. Okay. The classification boundaries could be more complicated than lines. Okay. Because, basically you can't necessarily separate in this particular class, as you notice. There is no single line that separates, the classes perfectly. So one dream, which we'll talk more about when we talk about nearest neighbor methods, would be that you found a way to carve up the space into chunks such that the point, which region you were in would tell you what the label was. Okay. But we are faced with but the tools for now that we have are logistic regression. So how can we use that idea to the ideas that we have so far to deal with classification in multiple classes? Now, in any of the homeworks that we did or projects, did you guys have a multi-class classification problem? Okay. I don't know if any of these guys did so far. Was there any kind of multi-class classification problem? A natural way to try to deal with it that turns out to be a bad idea is to represent the different classes by, again, right now with logistic regression, we got a lot of mileage from labeling the positive examples 1 and the negative examples 0. A natural generalization of this would be to have one variable that encoded multiple classes by distinct numbers. So for example, if we wanted to try to predict what hair color somebody was, we might have blonde be 0, brown be 1, red be 2, maybe black would be 3. Okay. What is a bad idea? Why is a bad idea a bad idea to label multiple classes? Or when is it a bad idea to label multiple classes by a single variable? Okay.
Well, when one is not more important than the other.
When one is not more important than the other, I'm not sure that I would say red hair is more important than blonde hair. Okay.
Yeah.
I would say all of them are better than gray hair, but that's a separate question. Okay. I think the point is when representing something by a numerical quantity makes sense if there is a kind of logical order to these things, a linear order to these things. Okay. So you might think like hair color, maybe there is a scale from lighter to darker. If there was a scale of hair from lighter to darker, okay, and that you were separating blondes from people with gray hair with people with full colored hair, maybe that makes sense. But generally speaking, there's not a linear order. I don't know what red, where, if I had a scale from darkness, I could see that blonde to brown to black is kind of a scale of darkness, but I don't know where red fits in. And I don't know where gray fits in. Okay, it means something different. Okay, now when you do have classes that are on a numerical, where there is a numerical scale, okay, then in fact representing the variable by a single numerical quantity is a good idea. Okay, often you might want to try to, like a classic problem in natural language processing is to try to maybe predict the review, okay, that someone will give a movie. So a typical a problem that people work on a lot was, could you read the review of a movie and try to predict whether they're going to give it 4 stars, 3 stars, 2 stars, or 1 star? You could treat that as a multi-class classification problem, saying there's 4 different types of movies: fabulous, good, fair, and terrible. Or you could treat it as the number of stars as being a measure of quality. Okay? If the variables have a natural, if the classes kind of reflect a natural order, then treating it as a numerical value, okay, I think is a better thing to do. Okay? And trying to predict the numerical value as a regression is a better thing to do. Okay? But otherwise, you're better off encoding them as separate, each class as being a separate class. The usual technique for dealing with these kind of things is to build one versus all classifiers. So we could, if we have an example here where we have 3 different types of points, we could use our linear classifier model technique, our logistic regression model, okay, and now produce what you call it, training example, and now produce, if we have 3 classes, reduce that to 3 different logistic regression problems, all of which are going to try to predict members of one class against all the other members, a one versus all or one versus rest classifier. Okay, so now we've got 3 different logistic regression problems. Okay, one for each of the classes, and we're going to try to see how well can we separate our members from members of a different class. Any questions about that? One way we could interpret this, again, our goal is for a particular value, what a new point, what is its label going to be? Well, each one of these classifiers, if these are logistic regression classifiers, for any other point, we'll say, what's the probability it was positive here? For this line, what's the probability that it was positive here? For these lines, what is the probability it was positive here? If this was the point that we were considering in all the examples, this one would have a higher chance of being positive in the 3rd classifier. And so we could say that the class we report is going to be the highest probability of any, the class with the highest probability here. Any questions? Are there any things about these one versus all classifiers, any issues that seem to come up? Okay, what is a bad thing about one versus all, or a limitation about this? Okay, sorry about that. I seem to be in some problem here.
It's slow.
One thing you're telling me is maybe it's slow. Why would it be slow? You're telling me that it's going to be k times slower than than a regular logistic regression, right? Because you're doing, if there's k classes, you're doing k linear classes. So it's going to be k times as long in training and k times as long in classification. That's true, I guess. Okay. Any other things that are unfortunate about this representation?
Unbalanced training data.
Because everybody see that we are, even if we started out and we were very, very diligent here about getting an equal number of members for each class. Let's say we did that. I'm now going to go be very diligent and make a equal number of each class. By the time we, by the time we label these things, if they were equal numbers to begin with, each one of these is going to have only k positive if it has x positive examples, there's going to be k minus 1 times x, negative examples. So this gets us into a world of unbalanced classifiers, okay? And we've got to then deal with it with the techniques that we have at our disposal. Any questions about that? Okay. The other thing that I would say that makes multi-class classification a lot harder, there's several of these things. One is to recognize if you have a classification problem with a lot of classes, okay, getting the class right is very, very hard. Actually, have any of you ever heard or dealt with a problem where there were a classification problem with a large number of classes? Are any of you familiar with any such problem? What is the ugliest classification problem you have seen? Yes? Okay.
There was once I did a document classification with almost 20 different document types.
You did document classification and you had 20 classes, okay? If you have 20 classes, the probability the monkey gets it right is only 0.05, okay? And what were those classes, if I may ask?
It was stuff like, is this a driver's license? Is this someone's tax return? Is this like their kid's high school?
Okay, okay, so we're saying driver's license, tax return. What other ones? Those are interesting classes. What other ones?
Bank statements.
Bank statements. What other things? Are these all forms?
Yeah, these are all like legal forms.
Okay, now which of these two seem like they are pretty similar? Were there two classes there that were very similar?
Bank statements and tax documents are surprisingly similar.
Bank statements and tax documents are very, very similar, okay? And one thing that's clear when you have a large number of classes, obviously if you're guessing, you're almost certainly going to be wrong. The other thing is, presumably in your world, okay, when you were doing this, did you have an equal number of examples of each type of document?
No, it was very unbalanced.
What was an example of a rare class?
People were not typically putting their driver's license in. We weren't asking for that very often.
Okay, so driver's licenses were rare documents, okay? And when you're building how many documents did you have a total in this company?
This was a large bank, so like thousands.
Thousands of documents?
I'd say like thousands of the small and then like tens of thousands of the larger ones.
Okay, so that was a good thing, okay? But bottom line, what are the problems that you have when you're dealing with these classes, multi-class classification? One is that that certain mistakes are probably more acceptable than other mistakes. Okay, maybe it was okay to call a tax return a tax document a bank statement, but you got in trouble if you called it a driver's license. Okay, and the other thing is that you're going to get into usually when you get to a big enough class, the minority classes there's very few examples of. 20 documents is an interesting class. In image processing, there's a famous example of ImageNet, okay, where they tried to build examples of what are you seeing a bird? What kind of bird? Is this a pigeon? Is this a duck? Is this a parrot? Okay. That in ImageNet, when I looked at it, there were 21,000 different categories. Okay, if you had to try to identify what was in a picture, trying to identify which was the right category for a particular label. If you're doing logistic regression, one versus all classification against 21,000 categories, the odds that you will get it right seems vanishingly small, and you're likely to make all kinds of different errors. So one idea that is a very, very powerful idea in classification is the idea of building hierarchical classifiers. Okay? You could try to do one versus all classification for 20 classes, maybe. Okay? But certainly for 21,000 classes, you would have a very, very difficult time. Much better is if you could group the classes into similar kinds of classes. Okay, here I have a classification on food. We know that it's probably hard to tell a piece of beef from a piece of pork. Okay, but it's probably easier to tell what a piece of meat is. Fruits and vegetables are another thing, greens. Okay. So you can imagine a world where if you have a large number of classes, one thing to do is to cluster the classes into natural groupings, so that if you cluster them into natural groupings, then the first level thing is what is the group? Which of the higher level groups is it that this object represents? Okay. Typically, it would be a lot easier to decide if something was meat, fruit, or greens. Okay. And if whereas if you got it wrong at the highest level, that would be a bigger problem. So building a hierarchy of your classes and building a classification, a classifier at each node of the hierarchy, okay, has the property that it reduces the problems to simpler problems. And at the cost that I guess running the class, I did this at the cost of, and then that when you want to actually do a classification, you're basically going to use the first level of the tree to decide which of the classes it is, and which is the second level classifier that you might use. Okay? Any questions about that?
How do you determine which categories to put them in? Like, categories that might look similar to a human might look really different to like the algorithm that's actually looking at the data. So how do you know you're choosing the most optimal categories for accuracy?
Okay, so this is a reasonable question. Okay, one thing is I happen to generally like human-driven categories. So if you have a taxonomy, I would say use it and try it and see how well it works. Okay, because I think that there's often a lot of wisdom in a human-built taxonomy. That said, what if you're not given a taxonomy? Usually the way to do it is by some kind of clustering. We'll talk about clustering, certainly in a class in the next one of the next upcoming classes. Okay, it may be next week, it may be next week, it may be within the next 2 or 3 classes. I'm going to talk a lot about clustering. What is clustering? What if you took your categories, okay, or your points of different types, and did some kind of an unsupervised clustering of them? Ideally, you would now have, these would be the underlying elements of each example. If you took all your examples, for now ignoring the labels, one thing you could do is to put them and cluster them into a certain number of groups. And then for every, you go back and interpret each cluster based on for each label, which cluster did most of my examples lay on? Does everybody kind of see that we could have an unsupervised clustering of the elements, and then interpret each of the original categories to decide which cluster it fell in, the bulk of its examples fell in, okay? And that would be a way to come up with a clustering like this. Does that kind of make sense?
A little bit, yeah. I just don't understand why that would be more accurate than one versus all. If the cluster is
One versus all, think of all the horrible things that are going to happen with one versus all when you've got 21,000 examples here. Now you've got a tiny bit of positive examples against a huge number of negative examples, okay? First of all, it's probably true that there may not be a single line that does a great job separating out that small negative example, that small group from everybody else, okay? That may not be another way to look at it. Suppose, let's go back to our, let's say that we had a world where we had, actually, what am I going to want to do? Let's say I have a bunch of different classes like, okay, maybe I'm doing a bad thing here. Let me make 9 classes. Suppose I had 9 classes represented by squares of tic-tac-toe boards, right? Does everybody see that, let's say, to try to build a logistic regression classifier to separate out class 5 from everybody else seems hopeless with a linear classifier? Does everybody see that that's right? You need to add nonlinear variables or something like that. But if we did this hierarchically, maybe it's not so bad. Maybe we first, if we had clustered our items into 3 different clusters, maybe based on rows. 1 cluster, 2 cluster, 3 clusters. Now, if we had done our linear separate, now there is a linear separator between these 3 classes. At the next level, there's another linear separator. You see that a 2-level linear separator would separate these classes, okay, in ways you wouldn't find if you did a one versus all thing. Does that make sense?
yeah, but I'm thinking if you're using a more complicated model like a neural network.
It could be, but I still will claim that you're searching for a needle in the haystack, okay? If you have 31,000 things of items, could you reliably tell a chimp from a gorilla? Okay, these are probably very, again, I hope I'm not offending any chimps or gorillas that are out there, but I'm going to guess that they are probably very, very similar looking. Okay, and that it's relatively easy to make that kind of a mistake. If I am given 21,000 classes, it's very, very easy to make a mistake. If I'm doing 21,000 different things, one badly fitted classifier could do something bad, okay? And so this is why when you have a large number of classes, I do believe hierarchies are a good thing, okay? And as we've seen, there's different ways of building that. Okay, any questions? One other issue that you need to keep in mind is that there is a difference. In an ideal world, we would have an equal number of training examples from every class. And you can imagine working very, very hard to try to attain an equal number of classes for each of elements of each type in your classification. That said, note that even if you have an equal number of training examples of each class, doesn't mean that the elements in the world are actually equally distributed. We once did a thing where we were building classifiers in Wikipedia based on try to predict what category somebody was in. And there are a large number of young, rock stars. There's very few rock stars, okay? But there's a large number of people who are, of the same age and rough disposition as rock stars are, okay? If you have classes where the actual population in the world, okay, is different, okay, you need to adjust your probabilities to reflect the prior distribution. This should be obvious, okay? You would like in your training example, maybe an equal number of terrorists and non-terrorists. But at the end of the world, when you're using your terrorist classifier, you don't want it to go off 50% of the time, okay? And your tool for avoiding that is Bayes' theorem, okay? If we have a prior distribution of what fraction of the world should be rock stars and should be terrorists, okay? This gives us a way to adjust what's the probability of someone being a terrorist given that our classifier said that they were a terrorist, okay? It will depend somewhat on the probability of someone in the world being a terrorist to start with, this being normally very low, okay? So you need a lot of evidence before you actually call them such. Any questions? The final thing I'd like to, this is not actually okay. The final thing that I wanted to say is that when you do the, the one versus all classifiers, you're going to end up with k classifiers, each one of which will give you a probability. Okay, the probability of being in class A might be 0.3. The probability of being in class B might be 0.4. The probability of being in the next class might be 0.3. Next one might be 0.2. These probabilities don't necessarily add up to 1. Okay, you need some kind of a normalization, some kind of an adjustment, okay, in order to convert these probabilities so they sum to 1. The simplest way to convert these independent probabilities to probabilities is simply to sum up the total weight of what you claim as your probabilities and use that as a normalization to divide each one of these things. If you sum these things up and get a value t, and then divide each one of these by t, the claim is the sum of them will be 1. So one way to do the normalization is just this kind of linear sum, dividing by a constant. The other thing, which I had put on my slide but didn't show I didn't upload it. There's also this function called a softmax, which will basically take something like e over t to the I divided by the sum of e to the t j, as j goes from 1 to the n. So the softmax thing takes these values, raises them to some power, right? Use that as the exponent for e, and then normalizes them in this manner. Okay, and this is typically done in let's say like neural networks and learning, because this is a thing that can be differentiated easily and stuff like that. Okay, but either way, note that you've got to take your classes, and they're not probabilities. Even though they're probabilities, they don't equally partition the space. You've got to normalize it in one way or another. Okay, any questions about multi-class classification?